Welcome to solverfy.
We're asked to show that the system of hydrostatic forces acting on a submerged plane area A can be reduced to a force at the centroid of the area and two couples. So the force P is perpendicular to the area and has a magnitude that's given there, and the couples are given, and we want to see how those equations were derived or came about. So we have our water level here, and then this is the y-axis that was given, the plane on which the pressure acts. So I guess if this was where the water was holding the water up, I have defined another axis here, y prime, just so that it's vertical. And then we have the centroid is some distance from here. Now it's 2D, so x in our case is out of the page here. And then so here's our surface, just a cross section of it, and we can see that we have a linearly increasing pressure acting over that surface. So generally y prime equals y sine of theta, where theta is this angle that the bottom makes with the water level. And then we know that the pressure is the specific weight, or the density times gravity times y prime, and that we substitute in, and so we get that the pressure is the specific gravity times y sine of theta. So what we need to do now is calculate the total force. So we need to integrate over the area. Okay, so obviously this is 2D. So we integrate over the area of the pressure. Okay, and that will give us the total resultant force. And a lot of these things don't depend on the area. So the specific gravity is independent of area, sine of theta is independent of area, so we can pull those out, and we get an integral of y over the area. And that, by definition, is the centroid times the area. So we get the expression that is given in the book, that the total force is the specific gravity times the distance along this axis to the centroid times a times sine of theta. Right? And so obviously this value here is the depth, okay, of the centroid. And now they're asking about the moments. So what we need to do to find the moments is integrate the pressure times a given moment arm over the area. So for the moment about the x-axis, which is out of the board, we have the centroid here, and we want the moment about the centroid, so we need the moment arms in this direction here. And so those are y minus y bar. Okay, so wherever we are here, we are at a certain y, and we subtract y bar off of it. So we have the specific gravity times the depth times the quantity y minus y bar, and we integrate that over the total area. We can expand that out, and we see that we get and pull out this factor, which is a constant, or not that factor, this factor, which is a constant, doesn't depend on the area. And so we get an integral over the area of y squared, and then minus y bar, which is independent of the area, or where we are in the area, and times the integral of y over that area. Now, we can recognize these things. This is the area moment about the x-axis, so the area moment about this point here, this axis coming out of the board, or the paper, and then minus, this is a times y bar, so we get minus a y bar squared. And that is the area moment about the centroidal x-axis. So again, we can use the parallel axis theorem, and this provides us with the area moment about the axis out of the paper at the centroid here. Now we have they ask us for the moment in the other direction about the y prime axis. Okay, so we have moments coming about this axis, so kind of out of the page, twisting, I guess, if you wanted to do a double arrow thing, moments like that. So those we need to figure out where the x position is of the pressure that's acting minus y bar. Okay, so we need to integrate this. The difference here, this is the moment arm that's causing this moment, and then we have to integrate that, multiply that by the pressure, and then integrate over the whole area. So we can proceed like we did before, and we pull this stuff out, which is not dependent on the area. Y bar is also not dependent on, well, at least where we are in the area. Obviously it depends on what the area actually is, but it is a constant. And so we get an integral over the area of x times y dA minus y bar times an integral over the area of x dA. Now again, we can recognize some things here. This is the cross area moment about the xy axis. Okay, so and then this is minus y bar times, and this by definition this is ax bar. And so if we look ahead in the chapter, we can see the parallel axis theorem extended to these cross moments is defined by this, and so this winds up being the area moment right here. This winds up being the cross area moment about the x prime y prime axis, or basically the axis. Well, this is still I shouldn't call it y prime, I suppose, because but anyway, this axis from the centroid, and then this axis out of the board, out of the pay for the x-axis. So let's actually call this, we should actually call this y double prime to make it distinguished from the axis that I defined vertically.